All right, so guys, like I was starting to say, good news, bad news here is we venture into our last section of the year. 12.3, we're going to be covering this today and tomorrow. But again, if you are feeling relatively confident with the difference quotient, the limit is h approaches 0 of f of x plus h minus f of x all over h, and you're feeling like, yeah, I've recognized the pattern, I know what I'm doing, the really good news is that that's all we're doing today. That's all we're doing tomorrow. The application is going to be different, but the pattern is the same. The math that you're doing is the same. We're going to structure our answer a little bit differently, yes, but ultimately it's the same. And like I said, that's phenomenal news if you're feeling really good about that stuff that we were doing yesterday, the homework that we just turned in. That's potentially bad news if we're not feeling very good about that. But what tends to happen, again, I'm speaking on behalf of previous years, what tends to happen is that if you're not feeling great about it at this moment, that's a very temporary thing. We just need to see more examples. Once you see enough examples to where it clicks, then it's like you're not going to be able to unsee it, sort of thing, right? That's my hope anyway. And again, as I got into yesterday, by the time we take our test, so by the time when do we go? We go Monday of next week. Is that correct? So by the time we're taking our test, this difference quotient stuff, guys, in all seriousness, it's going to be a strength. You're going to be feeling really good about this stuff. For some of us, we just haven't had enough practice at it yet. For some of us, you got enough practice yesterday, and you're probably feeling really good about it at this moment. But again, just please understand that the math is different as we venture into section 12 point, or excuse me, the math is the same. The application is a little bit different. Okay, especially with me kind of, I don't know, I trying to struggling a little bit with how I want to say this. I'm not going to let the way that the textbook sets the way that the textbook sets things up, I'm not going to let that dictate how I teach this stuff. So yesterday we already talked about what a derivative is. We already talked about how all we're really doing is finding the slope of the tangent line. Okay, like we addressed all of that stuff already. We're going to go a little bit further with it today. As you can see, it's kind of a weird title for a section. Section 12.3, the tangent line problem. But that's, again, hopefully we're already feeling decently confident with what it is that we're trying to do. Again, I guess what I'm trying to say is that a lot of the details that make section 12.3 we addressed yesterday. We talked about it within section 12.2. All right. So the goals that we have in mind here for these next couple of days: number one, students will be able to use tangent line to approximate the slope of a graph at a point. Number two, students will be able to use the limit definition of slope to find exact slopes of graphs. And then students will be able to find derivatives of functions and use derivatives to find slopes of graphs. So all of this sounds really new and unfamiliar, but I assure you, this is what we were doing yesterday. We were going to literally just finalize our answer in a slightly different way. Very, very slightly different way today. Also, what this is getting at, students be able to use limit definition of slope to find exact slopes of graphs. All that means is that when we get our final answer, we're going to tell you at which point we want to evaluate. So we have our final answer is, what was that last one? Like 1 over x minus 1 squared or something like that. Well, what if we told you, okay, now evaluate at the coordinate 7 comma negative 5? Well, I guess now we know x is 7, so we know what we're going to plug in, and we'll see what we get back. Does that make sense? That's hopefully we don't view that as, oh gosh, now it's hard. Hopefully it's just one more little thing. Okay? All right, so the tangent line, again, I'm very hopeful that all of this stuff is sounding familiar. As we addressed yesterday, kind of that overarching plan here is that we're trying to narrow in on how in the world we could find the slope of a curved line. Okay, which right now in pre-calculus, who cares? Why do we want to do that? But with where you're going in AP Calc next year, again, that's going to have big implications. That's going to have a lot of application as well. Is being able to approximate the slope of that curved line. That's going to be a big deal for us moving forward. So for all of those same reasons as discussed yesterday, that tangent line, we can identify a point that's on the curve, we could draw a tangent line through that point, and if we can find the slope of that tangent line, now we're narrowing in on parts of the curve. If we find enough of those, we could start to approximate the entire curve. From this point, from this x value to this x value, we know that our average slope is blank. We know from this point to that point our average slope is blank. That sort of thing. And that's going to be really important for us as we can zoom in and zoom out, so to speak, on these curves. Okay? So as we get into this, again, it's written in red, must be important. It says tangent line is going to be used to determine the rate at which a graph rises or falls. Typo. Rises or falls at a single point. And as soon as you're seeing rises or falls, hopefully you're thinking slope. We're talking rise over run. How much, at what rate are we doing this? Okay? We refer to slope as rate of change. So that's exactly what we're doing. We're trying to find the slope of these tangent lines, just like we did yesterday, right? We say that the tangent line to the graph of the function f at a point P, which is x1, y1, is the line that best approximates the slope of the graph at that point. Okay, what this means, what that translates to, is that with our toolkit that you have right now, we don't know how to find the slope of a curved line. We just don't. That's what a derivative is going to tell us, is the approximate slope of the curved line. So we have to algebraically find those things. And that's what we're continuing to do today. So what this all translates to, here's the definition of the slope of a graph. We say that the slope m of the graph of f at the point x comma f of x. Sounds weird, okay? But all that we're saying is that the slope at a particular point. Okay, so again, we know that these curved lines, or I guess they could even be linear functions, they have an infinite number of points. If we were to pick one, if you were to pick a point, isolate a point, and you wanted to find its slope, okay, that's going to be equal to the slope of the tangent line at that same point, and it's given by this. Now, this difference quotient that we were using yesterday was actually just from here to here. It was just the right side. Do we understand that all that's different today, the only thing that's different today, is that we're writing m equals? That's it. That's the whole difference. Yesterday, like I said, I don't know if I'm just couldn't get out of my own way or what, but I just feel like it's foolish to not introduce when we're trying to tell you what kind of like the purpose of why are we doing the limit as h approaches 0 of f of x plus h minus f of x all over h. Why are we doing that? I felt like that was the appropriate time to identify, hey, this is how we find the slope of the tangent line at a particular point. All that we're doing now is we're making that more formal by saying m equals this. So if you're looking for dramatically different math techniques, you're not going to find them today. It's the same thing. All that has to happen now is that where we were finalizing and we were getting an answer like 3x minus 5. Oh, yeah, great. There it is. Well, now today it's going to be m equals 3x minus 5. Okay, the other thing that potentially and probably will happen today is that not only are we going to be asking you to find this, but then maybe there's a part A that says, okay, what about at the point negative 2, 7? Well, do we know what x is now at that point? We could plug it in and we could go to work, couldn't we? That's it. Again, that's the new stuff for today. So really, more than anything else, if you're kind of on the fence saying like, I felt like I was kind of getting it yesterday, kind of not. Hopefully, we're viewing this as a positive. All right, hey, I have the opportunity now to practice a little bit more because the problems are going to be pretty similar to what we did yesterday. All right? So we've got all these diagrams that back it up, but I don't know how necessary that is. Okay? What we're saying is that we want to find the slope of the tangent. Where's the tangent line? Well, we want to generically find it. That's going to be in terms of x, and then we want to specifically find it at whatever they tell us coordinate-wise. All right? So here's the first one. We want to find the slope of a graph at the given point. So as we can see, the function that's provided, f of x is x squared. We specifically care about the point negative 2, 4. Okay, so there's a couple of ways that we could play this out. The way that we're going to do this initially is the way that we kind of traditionally always do. We're going to find the limit as h approaches 0 of our difference quotient says f of x plus h minus f of x all over h. Everything that we would have done yesterday, right? So we know that off to the side, we've got some work to do. We need to figure out what's happening top left, which means that we need to evaluate f of x plus h. Now my function, as you can clearly see, is x squared. What do we put in place of x? X plus h. We can do a little bit better than that. If I were to square this out, x plus h times x plus h, boiling this out, we're going to get x squared. Outside, inside, we're going to get 2xh. Last, we're going to get h squared. Nothing else combined, so this is f of x plus h squared. Or f of x plus h, excuse me. Okay? The one that's a little bit easier is when it comes time for us to figure out the top right. Top right is just given to us. The top right, we were told that f of x is merely equal to x squared. Not going to happen any easier than that. There it is. That's how this is going to work. So our task, what we were doing off to the side, is we wanted to figure out what we're going to put in place to the top left and to the top right, and we know those pieces now. So my side work is done. And all that we're doing differently, remember today, I almost dropped the ball already. We're finding the slope. So we're going to say m equals this whole thing. So in continuing with that, m is equal to the limit as h approaches 0 of, well, now we're saying that top left was x, or is, I should say, x squared plus 2xh plus h squared minus the top right f of x is given as x squared. This is all over h. All right, so if I were to pause here just for a moment, because I know that we had some people in terms of last night's homework that weren't feeling particularly great. Are we seeing what we've done up to this point? And if not, now would be like the perfect time to identify what it is that we're not seeing. Can I get like a thumbs up or thumbs down, something like that from each of us? Like, are we okay with this? A lot of people don't want to show me a thumb. Okay, all right. So what can we do now in the numerator? Or before you answer that question, understand why we can't use direct substitution. If I let h go to 0, we're going to have a 0 in the denominator. We can't have it. Okay, we know that. So at this point, once we've subbed everything in, at this point now, this is a dividing out problem. My task is to divide h out of the denominator. As soon as we can divide h out of the denominator, then we can use direct substitution, right? But we have to take care of that first. I can't use direct substitution until h is divided out of the denominator. We understand that part? Okay, so moving forward, let's get h out of the denominator. And the way we're going to do this is using our algebra techniques. I'm looking at my numerator. Some things are going to, well, a couple things are going to subtract out. Do we agree that x squared minus x squared, they're going to cancel out? Leaving me with 2xh plus h squared in my numerator over h in the denominator. Still can't use direct substitution the way that it sits, but what can I do in the numerator, please? I can factor out an h, exactly. So my slope is equal to the limit as h approaches 0 of, the h is factored out, h times 2x plus h all over h. Now have we done it? Have we been able to now say that we've divided h out of the denominator? Absolutely. So remember that my slope is equal to the limit as h approaches 0 of, now it's just 2x plus h. Now can we use direct substitution? Yes. So in doing so, wrong variable. 2x plus, we said that h is 0, and we've got it that my slope is 2x. Now, is that the whole task? No. We were asked, if we go back to the beginning of the problem, is to find the slope of the graph at the given point. So this is the slope of any point that we want. This is the generic, whatever point you desire, we could plug its x value in place and we're good. But we were specifically told at which point? Negative 2, 4. All right, so if we're trying to evaluate at negative 2, 4, what does x equal here, please? Negative 2. Put that in place. My slope is equal to, we said 2 times x, where x is negative 2. 2 times negative 2, can we say that my slope is negative 4 at that given point? And we have it.